In this video, we're looking at forces and the triangle of forces as an application of vectors. So a force is a push or a pull. Some examples are gravity, magnetic forces, friction forces, and air resistance forces. Objects under balanced forces are said to be in equilibrium. If the forces are balanced, then there is no movement. Field forces act without physical contact between objects, whereas contact forces are pushes or pulls exerted on objects due to contact. Resistive forces occur when two objects move or attempt to move relative to each other. A particle is used to model an object and is taken to be a point. For instance, the size of the object is not relevant, and any internal movements, such as spin and change in shapes, are not included in the model. In modeling motion, we make the following assumptions. Light, body, or string means that the object has no mass. Smooth means that no frictional forces are exerted. Inextensible means strings or ropes do not stretch. Rigid means that objects do not change shape when forces are applied to them. Perfectly elastic means that applied forces do not permanently deform an object, for example, a spring. In many cases, we ignore the presence of forces which would be insignificant, such as air drag or slowly moving objects. Force is a vector quantity. The unit of force is newtons. Newtons are given by N, so if I said something was 5 newtons in force, that would be written as 5N. Newtons represent kilogram meters per second squared. So that is a mass times an acceleration. Forces can be described in two ways, using I and J notation, for example, F equals 2I minus 4JN. Only coplanar forces will be considered, or using size and direction notation. For example, F is equal to 200 newtons at north, 45 degrees east. That would be a force of magnitude 200 newtons directed at an angle 45 degrees from north towards east. So the net or resultant force, the net or resultant force acting on a particle is the vector sum of all real physical forces acting on that particle. So we have some instances here where we want to draw vector grid diagrams to represent the forces involved in the situations shown below as a set of vectors acting on a point particle. Indicate the relative size of the force by the length of the vector arrows. Further indicate the nature of each of the forces acting by labeling W for weight, N for normal contact, F for friction, A for applied force, and D for air drag or air resistance. So looking at point A, we have a stationary person. They're not moving. They're going to have a weight to them that is applying onto the ground. But they aren't sinking through the ground, which means there must be an equal force holding them up. That is the normal contact. So this is our vector N, and weight is our vector W. For B, we have a constant velocity. When looking at our particle, we're going to have the weight of the car. It's not going through the ground, so we're going to have a normal force. It's going to have some air drag because it's in motion. But then it's also going to have an applied force of A. Notice that the A and D vectors have been drawn equal to each other. The applied force is equal to the drag force, which means it isn't accelerating. It is at constant velocity. In my next drawing, I'm going to draw these same lines However, now my applied force must be longer than my drag force. Now it says here F for friction or D for air drag or air resistance. Technically, that D vector would also have some friction from the tires on the ground. A cricket ball through the air, it's going up and to the right with constant velocity, which means the applied force and the air drag, oh, that's too long, and the wind drag, D, are going to be equal to each other, equally acting on our particle. For a ball rolling down a slope, we have our particle. It is going to have a weight to it. It is going to have a normal force, not coming directly up, but coming perpendicular to the slope that it is going down. So that is our, not our friction, sorry, our normal force. It will also have friction, slowing it down as it goes down the slope. However, the friction and the normal weight is not enough to counteract, and the normal force is not enough to counteract the weight. It is rolling down that hill. And then lastly, we have our parachute person. They are falling due to their weight. However, they are falling at constant velocity, which means the air drag from their parachute must be equal to the weight. So, looking at example 26, three forces, F1, F2, and F3, act on a ball as shown in the force vector diagram. The three forces are described by the vectors F1, F2, and F3. Determine the resultant force R, the sum of the three forces F1, F2, and F3. So, finding R is equal to the sum of F1, F2, and F3. Therefore, R is equal to 4i minus 5j plus 10i plus 2j minus 6i plus 7j. Grouping our like unit vectors, we're going to get 14i minus 3j. 14 minus 6, which would be 8i. And then negative 5 plus 2 plus 7 is going to be negative 5 plus 9, which is going to be 4j. So 8i plus 4j. It's going up and to the right. Determining the magnitude of this resultant force is going to be the square root of our x component squared plus our y component squared, which is going to be 64 plus 16, which is the square root of 80, which is the same as 2. Oh, actually, we can take out 16, so that would be 4 square root 5. But because we're talking about a circumstance that has units, so newtons, we could express that as a decimal. However, because we haven't really been asked to talk about it in terms of newtons, we're going to leave it as just 4 root 5n. Okay, part C. We're asked to determine the angle that the vector r makes with the I vector, so the angle to the positive x-axis. We know that this can be found by using the dot product of r and the I vector. So the angle of r dot I will give us the angle it makes with the I vector. So we divide that by the magnitude of both vectors, and that will give us the cosine of the angle between r and I. So that just comes from the second definition of the dot product. So the dot product of r with I is just going to be the x component of r. So that's 8. Then we're going to have that over 4 root 5. And to find theta, we want to take the inverse cosine of that ratio. And that gives us an angle of 26.6 degrees. Part D asks us to find the force F1 is changed so that the resultant is equal to 0. That is, the resultant forces equal 0. Determine the force F1. So if we have this value of R2 that is equal to 0, we need to know how much smaller must our F1 force be. So we take F1 and we subtract the initial value of the resultant. So that is going to be equal to 4I take 5J subtract 8I plus 4J, which will give us negative 4I minus 9J. Another way we could do that is look at this original value of R, F1 plus F2 plus F3, let that equal to 0, and then rearrange to make F1 the subject. So F1 would be equal to negative F2 minus F3. Okay, so looking at three non-parallel forces acting upon a single particle can have a resultant force of 0. That is to say, the resultant of this x, y, and z vector is equal to 0. If that is the case, then these three forces can be represented in a triangle, since the sum of the forces is 0. This allows us to use the sine and cosine rule to solve problems. So, in example 27, we're given three forces, A, B, and C, act on an object such that the resultant force is 0. The force A acts at an angle of 150 degrees to the force B, and they have the same magnitude of 20 newtons. Determine the magnitude of C and calculate the angle that the force C makes with B to the nearest degree. So we have the magnitude of A is equal to the magnitude of B is equal to 20 newtons. We also have that the angle between those two forces is 150 degrees. So if we have A, B, and C acting upon this single point, we know that we have some vector A coming up here, then to the left of it, 150 degrees away, we have some vector B also acting upon the same point, and then we have a third vector going in the opposite direction to those two with unknown magnitude. So we have to determine what is the magnitude of C. So based off this rule that we've been given, we turn it into a triangle with the angle between A and B being 150 degrees. So let's actually consider this a different way. If it's 150 degrees when put together like this, when combined to make a triangle, we're going to have to subtract that away from 180 degrees. So what we're essentially doing here is taking these three arrows that are pointing out of the particle and lining them up so that they touch head to tail. So I take that, let's undo that. So I take that vector B and I transpose it so that it's coming out from A. And I take the vector C and I transpose it so that it's coming into the tail of B. This gives me that triangle that I was looking for. So we're going to have not 150 degrees, but 30 degrees between A and B. We're going to have the magnitude of A and the magnitude of B, so we can use sine rule, cosine rule to find the others. So determining that, we've got a triangle that goes 30 degrees from each other with one final point. We know that the magnitude of both of these is 20 newtons. So applying cosine rule, we get that c squared, which is the magnitude of c, is equal to 20 squared plus 20 squared minus 2 times 20 times 20 cosine of 30, which gives us 107.18, which means capital C is equal to 10.35 newtons. So the magnitude of C is 10.35. We're then asked to determine the angle that the force C makes with B to the nearest degree. So to do that, we use the sine rule. So A over sine of capital A is equal to B over sine of capital B. So this is for part B, which means that 20 is over sine of 180 degrees, take theta. Right, so theta is the angle between B and C. So that's this angle up here. So when put into our triangle, again, we have to apply the supplementary rule. So what we're currently solving for is 180 minus the angle we're interested in. So then when I let that equal the 10.35 newtons over sine of 30 degrees, we can rearrange to find that 180 take theta is equal to inverse sine of, so rearranging the other properties gives us inverse sine of 20 sine 30 over 10.35. And then that means that theta is equal to 104.94 degrees. So the angle between B and C is approximately 105. Now, it would be lovely if we were allowed to do this on our external exam. However, QCAA does not accept sine rule and cosine rule as a valid answer to a question like this. So instead, we have to take these vectors, bring them down into their I and j components, and then solve for the resultant that way. And that's something that we'll be looking in for the start of our lesson on Monday. Thank you very much for watching this video.